All right, everyone. So I forgot to turn the microphone on when I gave this lecture in class, so I'm doing a narrated PowerPoint presentation for this, and I'll put that same thing up on my YouTube channel. But of course, you know this by now because you're watching it on my YouTube channel. So the topic on the 10th was the Clean Water Act and biotic integrity. So the Clean Water Act came down in the 1970s along with a lot of other environmental legislation, and there hadn't been a whole lot going on up until then as far as keeping our waters clean. There have been a couple of pieces of legislation here and there, the Federal Water Pollution Control Act in 1948, and it had attempted to help manage clean water, but it only applied to waters that flowed across state lines, and it allowed the Surgeon General to step in only when human health was severely threatened. So there was actually a case of the Chicago River that flows into Lake Michigan, and the city of Chicago's drinking water intake is in the lake, and so an awful lot of sewage waste went into this river, and so there were cases of the drinking water getting contaminated. So the Chicago River was actually had its flow reversed, so that it flowed from Lake Michigan out instead of into Lake Michigan in response to this. And so now the Chicago River has other chemicals put into it. This is what happens on St. Patty's Day. This green dye that's put into the river and makes everyone feel all St. Patty's Day-ish. But the Clean Water Act was the piece of legislation that consolidated all authority for water pollution under the administrator of the Environmental Protection Agency, who's currently Andrew Wheeler, who may be a step up from Scott Pruitt, the first EPA administrator, but anyway, has a history of some lobbying for fossil fuel interests, and so the EPA hasn't been doing a real great job of protecting waters lately. But what this Clean Water Act did was it made discharge of any pollutant into navigable waters illegal without a permit. And now the good news is that even waters that aren't navigable often flow into waters that are. So by extension, it protected a lot of water all across the country. So here's the goal. The goal of the Clean Water Act is to restore the restoration and maintenance of the chemical, physical, and biological integrity of the nation's waters so that they can support protection and propagation of fish, shellfish, and wildlife, and recreation in and on the water. So you see this focus on the word integrity, and we'll talk about that later, but the idea is that each of these rivers or streams should be true to something. It should be true to like an idealized body of water. And so the Clean Water Act charges states to essentially monitor their surface waters and make sure that they're true to the standard that they should be able to meet. So if you think of biological integrity, right, it's whether or not this river or stream is true to like a standard of quality. And you think of all the things that can affect biological integrity. This is a figure from your book. It's pretty much everything. So we can talk about the character of the channel, right? That as we change the substrate, the sinuosity, if we channelize streams, if we mess with the canopy, the channel morphology, the gradient, temperature, all these different things will affect biological integrity. So biological integrity consists of the species being able to live there, right? So any changes on these different axes that I'll show are going to affect what's able to live there. Energy sources, sunlight, nutrients, seasonal cycles, primary, secondary production, and organic matter input, that also is going to change. And of course, as we learned with the river continuum concept, that's a real important piece to how these ecosystems function. All those biotic interactions are going to be influenced by many things. Flow conditions, how natural is the flow regime? Has it changed? If so, well then different species are going to be able to live there than were there previously. And then maybe what we think of first when the idea of water pollution comes to mind, the chemical variables. How are the chemical species in that river and stream going to be affected by change over time? And if they are affected, of course, then they'll affect the species that live there. So changes to all of these factors are going to affect the species that are able to live in these streams, and hence the biological integrity of these streams. So how well has it worked? Well, so there's a paper that came out last year where these authors examined the legacy of the Clean Water Act, how effective it is. And so, to quote this paper, it said there are three main findings. First, water pollution concentrations have fallen substantially. And between 1972 and 2001, for example, the share of water safe for fishing grew by 12 percentage points. So for water to be deemed safe for fishing, of course, it has to be at a certain standard of quality to make the fish safe to eat. Just a graph from their paper that shows the dissolved oxygen deficit. So if you think about what affects dissolved oxygen in streams, it's not only consumers that use oxygen, but also decomposition. Decomposition of organic matter burns up oxygen. And so in rivers and streams that have had a lot of nutrient input, and in particular sewage input, there's a lot of decomposition of organic matter that happens, and that burns up oxygen. So as that is cleaned up, the oxygen deficit will decline. So again, since 72, the dissolved oxygen deficit in these surface waters has declined, and the share of waters that are not fishable has gone from almost 40% back in the 60s to less than 20% now. So, you know, I think sometimes we forget the long view, and we just see problems now, and we want those to be solved. But in fact, when you look back over the last 40, 50 years, 60 years, stream quality in the U.S. has been getting better, for sure. All right, so the Clean Water Act was pretty effective at eliminating point source pollutions, especially from wastewater. And again, wastewater was what led to that real high biological oxygen demand. And so recently, however, there have been a couple shifts in application. One is that there's been a focus on the physical and biological integrity of the streams rather than just chemical. So in other words, instead of trying to quantify chemical pollution, there's been a movement to look at the species that live there that are what you might call emergent properties of the ecosystem and sort of represent the overall quality. Because if you imagine a stream that's subjected to chemical pollution just every now and then, you might not catch the chemical contamination unless you're sampling at the exact right time. But the species that live there will have to deal with it all the time. And so if you find species there, if you don't find species that are intolerant of pollution, then you can infer that this area has been polluted from time to time. And the second is a focus on what we call wet weather pollution sources. So the non-point runoff. So the runoff of those impermeable surfaces in urban watersheds. Of course, the runoff from the agricultural land in those agrarian watersheds. That we've gotten pretty good at cutting down on points of high pollution levels, but now really what's affecting the quality of our nation's rivers and streams is runoff from these sort of wet weather events. Just to show you an example of what that looks like, Smith Mill Creek. So this is a map of West Asheville, Highway 23. There's Patton Avenue going from left to right, and then it crosses over the French Broad there on the left, the Bruce Bowen Bridge. And you see that little pin there where it says Group 3. This is actually an activity that our fish ecology class did several years ago. So we went out there to sample the stream. And this is Smith Mill Creek. It flows down Leicester Highway until it meets Patton Avenue, and then it flows behind Patton Avenue That's where Group 1 sampled it. They were right there. This place was like a KFC there on the corner of North Louisiana, or on the corner of Louisiana Avenue. So we pulled up to the site, and it's kind of a sad little stream, but it at least the water's clear, right? So we started collecting some data, measuring stream width, learning a little bit about this spot. So you can see there's a lot of sediment there in the center, which is a little bit concerning. That suggests that there's some erosion going on nearby, but the water's not bad. Then the heavens just opened up and dumped down on us, and it just rained like crazy. And so all of this water came off of these impermeable surfaces. And then this happened. This is, one of those storm drains, which you've all seen, those grates on the side of the road. Sometimes they have a little fish picture next to them, and it says drains directly to the river. Well, all of a sudden, this black water just started pouring in from these storm sewers. And then down below, you can see some muddy water coming in overland along a little ditch. And so all of a sudden, the stream went from something that looked kind of sort of clear to just this dirty torrent of nasty water. And so all of a sudden, there is a very different habitat. And so now we start to see that the species that can live there are only those that are able to handle pollution. And that this stream was doing okay until this big rain event came along, this big wet weather event. Okay, so how does the Clean Water Act work? So it has two main areas of emphasis. One is on restoring degraded waters. The other is on maintaining quality of pristine waters. So this is how it's set up in the big picture. So we begin by establishing some water quality standards. Those have to do with what are called designated uses. So essentially, every river and stream has to be given a designated use. What is its purpose? And then those designated uses carry certain water quality criteria with them. So I'll show you a couple examples of those in just a second. And then the state has to monitor those rivers and streams to see if they're meeting the criteria. So these water quality standards apply to all the different surface waters of the U.S. And the first part is designating a use for those waters, as I said. And the next part is water quality criteria. And those are, again, tied to these designated uses. Whoops, I'm sorry, that's actually in the wrong spot. So the water quality criteria are these numerical descriptions of conditions in a water body necessary to support the designated uses. So I'm sorry, that red polygon there should be over water quality criteria. And then anti-degradation is just the idea that if you have streams that are meeting the criteria, you have to keep them from becoming degraded. So what are those designated uses, sometimes called desired uses? Things like this. So on the top is the most extreme, the strictest criteria, so drinking water supply. If you've ever driven on I-40 towards, up past Swannanoa, up towards Old Fort, you'll see a sign that says drinking water supply area. Report any kind of chemical spills, right? So rivers that are designated drinking water supply, very high criteria. Similarly, any kind of streams that are going to be designated for water-based recreation, including full body contact, swimming, anything that you're going to be catching fish from, those are all going to have fairly high water quality standards associated with them. But then you can see further down, agriculture water supply can be a designated use, industrial water supply can be a designated use, and clearly for those kinds of uses we wouldn't have to have the same high quality standards of water. Okay, so once those water quality standards are established, then monitoring happens. And if they're meeting the water quality standards, you come over to yes, and then it comes over to apply anti-degradation, right? So we just try to keep it preserved. But then on over to the left, if those sites aren't meeting the water quality standards, then that river or stream gets placed on the naughty list, also known as the 303D list. Those are known as, or what are known as, impaired water bodies. So if a river or stream doesn't meet the water quality standards and it goes on that 303D list, then you have to look at what pollutants are affecting it negatively. And so you have to come up with strategies to reduce that pollution, one of which is called the total maximum daily load. So for instance, with sediment, you might come up with a total maximum amount of sediment that's allowed in a day. So you have to come up with these standards to help meet those criteria. And then if those, to help meet those criteria, there are a series of grants over here on the left where it says Section 401, Section 404, Section 319, NPDES. Those are all sections of the Clean Water Act that allow for funding to kick in to help streams that are on the 303D list. And so these can fund activities like stream restoration, like purchasing conservation easements in the riparian zone, these kinds of things. Yeah, so those are all tools that can be used to reduce pollutant loading. So we've been to the Swannanoa River, which is actually an EPA success story. This is a picture from a site near Old Highway 70. This is the slipperiest site I've ever sampled. I took one fish ecology class there, and all of us fell into the river at least once. These are a couple students probably holding on for dear life so they don't slip in. You can see that bedrock. It was just so slick, it had algae all over it. But one of the fishes there is a Swannanoa darter. It's kind of cool to have a fish named after a river nearby. So this is a map of impaired rivers, so river sections that were on the 303D list. And what I'd like to point out here is that the Swannanoa is, so Buncombe County is the county in between three. So it's the second up of the three counties in the middle. It has several dark colored. See, maybe I can use my pointer to show here. So this is Buncombe County right here, and this is the Swannanoa River. And so you can see portions of it were listed on the 303D list in 2006, but not in 2010. And so if you remember those restoration structures that we saw in Beetree Creek and in the Swannanoa, that work was funded through the 303D list. Now the French Broad River, downstream from Asheville, is on the list. It has some fecal coliform issues because in Woodfin here, we have of course our municipal wastewater treatment plant, and the quality of the French Broad drops down below there. We also have Hominy Creek in here. Let's see, Sandy Mush Creek I think is on there as well. But anyway, the good news is Swannanoa was not on that list in 2010, but it was in 2006. So unfortunately, it's back on the list. So this is the list from 2016. Swannanoa River from its source to the North Fork of the Swannanoa River. So this is up in Swannanoa, not coming down into Biltmore in that area. But you can see it only received a fair rating. So when you use this benthos sampling protocol, if it receives a rating of fair or below, so fair or poor, anything like that, then it has to go on the 303D list. And so this is based on benthic samples. So so literally based on the aquatic macroinvertebrate samples, it failed the rating. So it's back on the list as of 2016. All right, so we can come up with ways to try and measure biotic integrity, and this is a topic that we'll mention for a couple class sessions in the future. So for instance, you can look at the EPT taxa richness. So EPT are mayflies, stoneflies, caddisflies. those are orders of aquatic macroinvertebrates that are, on the whole, generally intolerant to habitat degradation. So the more of them you find, the better shape your stream is going to be in. So this is taxa richness, so literally number of species of mayflies, stoneflies, caddisflies. And so you can see you have to calibrate it different for different parts of the state. So in the mountains, if we get over 35 taxa, we would characterize the stream as an excellent shape. In the Piedmont and coastal plain, it's lower. So in the coastal plain, if you get 23 or more, it's an excellent shape. But that many taxa in the mountains would only be good to fair. So you can see that in general, the habitat quality is higher in the mountains than in lower elevations. But so it sets the standard higher, right? So for a site to be considered excellent in the mountains, we've got to have 35 EPT taxa, whereas it's only 23 in the coastal plain. So this is one of the criteria that is used. And again, if the stream is categorized as fair or poor, then it can go on that 3 or 3D list. Okay, so when you use an index of biotic integrity, it's challenging because you have to calibrate it for different areas and different regions. So there's a couple issues with this index in North Carolina. One of them is that it may not measure impacts due to sediment. The problem is a lot of these disturbances are only are sort of fleeting, right? So if sediment is deposited and really disturbs the site, if you're sampling at that time, you might find the impacts, but then a big flood comes through, washes that stuff out, and you won't find it. So if you're looking for impacts of sediment, which is the largest water quality issue we have in the US, you're not always going to be able to find that, especially if there's been a period of scour. There's always a challenge of like which set of criteria you will use, right? Because there's no clear line between the mountains, the Piedmont, and the coastal plain. So, you know, when you're in the mountains, but you're getting closer to the Piedmont, a little lower elevation, when do you switch over, right? Because that could have implications for whether a site lands itself on the 3 or 3D list or not. So that's a challenge. Another issue has to do with our high altitude mountain streams. So as we showed earlier, the idea is that the more species of mayflies, caddisflies, stoneflies you have, the better the quality of the stream. But the problem that you have is that in some rivers and streams in the mountains, they're not very productive at all, really low rates of productivity. So, and that's because the geology of these river basins is igneous or metamorphic. And so you don't have the natural nutrient input, particularly of phosphate ions, that you would have if these rivers were rising out of sedimentary rock. So because of that, some of these high altitude mountain streams can have very low numbers of aquatic macroinvertebrates just because there's low productivity. The streams are very clean, but they still produce very low numbers. So that's another challenge. So anytime you apply an index like this, you kind of have to be aware of issues that might make it tough to interpret them. Oh yeah, and then this as well, sorry. And then the other part is that when the numbers of mayflies, caddisflies, and stoneflies are very low, a lot of what you may be finding could be drift organisms. You'll look in the lecture for the data a little bit later and learn about drift and the fact that a lot of aquatic macroinvertebrates drift, both behaviorally and in response to high flow. And so if you're sampling an area without very many, there's a chance that those could simply be drifting organisms that have come from upstream. And so they may not truly be representing the habitat quality at that site where you're collecting them. So this idea of integrity then, right, is pretty key. Thinking about this is kind of important. All right, so this question of how to measure integrity is an important thing to think about then. So we've mentioned this idea of looking at, for instance, mayflies, caddisflies, and stoneflies, which are intolerant And in general, how we want to do this is to try and compare a chosen site with a reference site. And you can either compare the community directly with something like an index of biotic integrity, or you could try and use the physical parameters of the site to predict what should be there, and then you can compare it to that. And so this is an example of an index that was developed using fishes. And so there are several different metrics that one can measure on the left side of this figure here. And then an idea of where those values would be, low versus high biotic integrity. And so, for instance, with fishes, we find that darters are more to the high side, sunfishes to the high side, suckers to the high side. Intolerant species, we can certainly classify fishes as intolerant, just like invertebrates. But then other things that might be fall more on the low side of biotic integrity. So green sunfish, for instance, are a very tolerant species. They might be more on the low side. Omnivores, in general, are able to live in more habitats because they can live different ways, eat different things. And so they're sort of an indicator of low to medium biotic integrity. Piscivores, more to the high end, because they need an intact food chain to support them up at the top of the food chain. The overall number of species should be, can vary. And then the percent of fishes that are hybridized, there's generally more of those at low integrity, and percent that are disease low integrity. So the idea is you can go out and measure these things, look at the numbers you get, and say, hey, all right, what can we say about the quality of these sites? And you can do a similar thing for invertebrates. So this is an index that we'll actually use in lab. And so you can see we have different orders here. So Plecoptera, we got stoneflies, mayflies, dragonflies and damselflies, caddisflies, etc. And then they're broken down by family, and each family has a tolerance value associated with it. The lower that tolerance value, the more intolerant that family is. And so, you just kind of look it over, but you can see the stoneflies, for instance, are quite low. Got a bunch of zeros, ones, couple twos. The mayflies, we've got a couple that are more tolerant. We've got a couple sevens, we've got some ones, we've got some fours. Odonates, some are really tolerant, some are not tolerant. Caddisflies, there's a mix. And so the idea is we don't have to just go to order, we can go to family to get a little more detail. And then some different, so the fly larvae in Diptera, Chironomidae, which is 8, is quite tolerant. There's a couple that are relatively intolerant. Athericidae, I've never seen that, to be honest. Blephoroceridae are these sort of fly larvae that have suckers on them that stick onto stones. They're real cool, but I haven't seen that much either. So the idea is we could also assign tolerance values to these families and say the more of these intolerant families you see, the more pristine the site should be. So again, these indices of biotic integrity were first developed using fishes and later added in vertebrates and algae. Fishes, I think, at first because we had a good knowledge base for, their natural history, how tolerant they were, that kind of thing. But fishes do have some downsides. As we discussed in class, they don't live everywhere. They're not as abundant as aquatic macroinvertebrates. And they're more mobile, right? So if you catch fish at a certain site, you don't know that it's lived there for its entire life. So the problem is it may be in a poor quality habitat, but it might just be passing through, right? Whereas with macroinvertebrates, they're a little more sedentary. So they're a little better indicators of what the quality has been like, over a little bit longer term. Although remember, most of the aquatic macroinvertebrate insect larvae, they won't be in that stream more than a couple of years at the most, so maybe a year. So, but in a way that's good then, because it's sort of resetting the criteria each time. So you just think of different organisms and the costs versus benefits of using each of them. It also takes more time to sample in macroinvertebrates, take them back to the lab and ID them. Whereas you might have noticed in lab with fishes, we can just identify them right there in the field and put them back. So a little less effort involved with fishes. Yeah, we just talked about this already. Yeah, so just be thinking about like what would be the advantages and disadvantages of using, say, fish versus invertebrates versus algae when developing our indices of biotic integrity.